Okay, we are going to be doing the electric forces and fields problem, or electric fields and electric potential energy problems. First thing we're going to do is write down the equations. So first equation is E equals F over Q. So that's electric field equals the electric force over the charge. We also have the electric field equals K, which is still the same constant, times the charge that's creating the electric field divided by the distance from that charge squared. And our last equation is going to be the change in electric potential energy. We'll call that PE sub EL equals negative Q, which is the charge, times E, the electric field, times D, and that's the distance the charge moves. And this one's going to be tricky because the electric field and the distance, or that's going to be displacement, are going to be vector quantities, and so we're going to have to worry about the directions in those. So let's define what all the variables mean. E, the electric field, and that's measured in newtons per coulomb. F is still electric force, and electric potential energy is going to be measured in joules. Everything else is still the same. K is still 9 times 10 to the 9th. Q is still charge measured in coulombs. And D is going to be the distance or displacement measured in meters. So we'll be doing the first 5 problems together. So let's look at problem number 1. Problem number 1 says the electric field at a point 0.45 meters away.
Good morning, with Tony.
Sorry, the announcements got in the way there. So number 1 says find the electric field at a point 0.45 meters away from a 4.5 microcoulomb charge, and is it pointing away toward or away from the charge? Side. And we're going to use for this one, so we have Q is equal to 4.5 microcoulombs, which is 4.5 times 10 to the negative 6 coulombs. And we have our distance from the charge is going to be 0.45 meters. So the equation we're going to use, distance is going to be 0.45 meters, and we're going to use the equation electric field equals K Q of the distance squared. So K is still 9 times 10 to the 9th. Q is going to be 4.5 times 10 to the negative 6 coulombs.
Good morning, Kelly.
It's going to be 4.5 times 10 to the negative 6 coulombs, and the distance is 0.45 meters quantity squared. When we do that math, we are going to get 2 times 10 to the 5th newtons per coulomb. And now we need to figure out if that's pointing toward or away from the charge. Now remember, electric field points in the direction a positive charge would move if it was brought near the charge we're talking about. So we have our charge here, and it's positive. So if we brought a little positive test charge, that would be moving away. So our electric field is going to be pointing away from the positive charge we have there. Right, next we'll be doing problem number 2. So number 2 says an electric field of 580 newtons per coulomb is pointing to the right. What is the force a particle with a charge of 9 microcoulombs experiences in this electric field? Be sure to include the direction of the force. So we have electric field equals 580 newtons per coulomb. We have our charge is 9 microcoulombs, which is 9 times 10 to the negative 6 coulombs. And we're looking for the force that charge experiences, and also the direction. We'll find the force first, though. So the equation we're going to use is
Good morning.
So the force, electric field, equals F over Q. So we're going to do 580 newtons per coulomb equals the force we're trying to find, over the charge of 9 times 10 to the negative 6th. We multiply those out, we're going to get our force equal to 5.22 times 10 to the negative 3rd newtons. So now we need to figure out if that's pointing to the right or to the left. So the field points to the right, and we have a positive charge. So remember, the field points in the direction the positive charge would move, so this force is going to be pointing to the right. Alright, we're now going to move on to problem number 3. Problem number 3 says 2-point charges are 16.2 centimeters apart and have charges of 5.7 microcoulombs and negative 5.7 microcoulombs respectively. What is the magnitude of the electric field at the midpoint between the two charges? So I'm going to draw this out a little bit. So we're going to have a positive charge and a negative charge, each 5.7 microcoulombs. We're looking at the electric field at the midpoint between those. So we want to figure out the direction each electric field is going, and then whether they're going to add them or subtract them. So positive charge is going to be pointing away for the electric field because it points away from a positive. The electric field is going to be pointing toward the negative charge. So they're going to be going both in the same direction, so we're going to find the electric field for one of them and then add them together. So what we're going to do, we're going to use, and they're equal, so if we find it for one, we can just multiply it by 2. So I'm going to say electric field equals KQ over the distance squared. And our distance between both of them is 16.2 centimeters, so that's going to be 0.162 meters. So electric field is going to equal 9 times 10 times 10 to the 9th times the charge is going to be 5.7 microcoulombs, so that's going to be 5.7 times 10 to the negative 6 coulombs, over the distance to the midpoint is going to be 0.081 meters, quantity squared. So when we do that, our electric field for one of them, so we multiply or do that math, we get 7.8 times 10 to the 6 newtons per coulomb. So now all you need to do is multiply that by 2, because they're both pointing in the same direction. There's 2. So we're going to say times 2. And our final answer for the total electric field is going to equal 1.56 times 10 to the 7th newtons per coulomb. And our diagram up there would be pointing to the right, but we didn't have a direction on that, so we're just going to say the absolute value, or the no direction associated with that. Alright, we're going to do number 4 now. So this one says an electron moves 5 meters in the direction of an electric field of strength 320 newtons per coulomb. Determine the change in electric potential energy. So what we know here is we know the distance it's going to move is equal to 5 meters. The electric field strength is 320 newtons per coulomb. We also know the charge of the it's 1 electron, so the charge of 1 electron is 1.6 times 10 to the negative 19th coulombs. And we're looking for the change in electric potential energy. So the equation we're going to use here is the change in electric potential energy equals negative QED. Now the tricks on these is that if the electric field and the distance it travels through are in opposite directions, one of them has to be negative. But in this case, the electric field is pointing this way, and removing the, sorry, erase that, removing the electron in the same direction. If they're in the same direction, both of them are positive. If they're in opposite directions, you're going to have to make one of them negative. And we'll look at that on the next problem. So we plug our numbers in, we get 1.6 times 10 to the negative 19th times electric field is 320 times our distance is 5. When we multiply that out, we get our change in electric potential energy to equal 2.56 times 10 to the negative 16th joules. And that's positive, so the electron gained that potential energy. And if you think about it, to create this electric field, we'd have to have a positive charge over here. So if we bring the electron away from that positive charge, to generate that positive charge, would be generating an electric field that's pointing away from it. So if we brought the electron away from that positive charge, it's gaining potential energy because it's going to want to go back toward it. So now we're going to move on. So an electron moves 5 meters in the opposite direction, so our distance is equal to 5 meters. Our electric field is 360 newtons per coulomb, and charge is the electron again, so it's 1.6 times 10 to the negative 19th coulombs. And we're looking for the change in electric potential energy again. So, same equation. However, this time we have the electric field pointing one way, and our electron is moving the opposite direction. So we're going to have to make either the distance of the electric field negative, and if they're in the opposite direction, I will always make the distance negative. So again, we're going to use change in PE equals negative Q times the electric field times the distance. One thing I forgot to do in the last slide is Q should have been negative for the electron, and the electron was negative as well. I canceled them out right away. Probably shouldn't have done that to make it, or it would have been clearer if I had shown you that. So our Q, so we have negative times negative, and this should be negative up there. 1.6 times 10 to the negative 19th times the electric field is 360 times the distance is 5 meters. And when we do that math, we are going to get negative 2.88 times 10 to the negative 16th joules. And so that negative means it's lost energy, because if it moves this way, so we had a positive charge here generating the electric field, if it's moved this way, it is losing potential energy because that's the way it wants to move, and it's not gaining electric potential energy by moving away. Number 5, last problem we'll do together here. Number 5 says an electron moves 5 meters in the opposite direction to an electric field of strength 360 newtons per coulomb. Determine the change in electric potential energy.